Okay, let's use Boyle's law, Charles' law, and the combined gas law. Let's use what we know in the sense of how they work, what the law states, into a mathematical problem. First thing you need to do is just sort of need to recognize which law you're dealing with, and then you're able to apply the math to it. So, for example, the first problem states that a sample of argon gas has a volume of 118 milliliters. The pressure is 84.9 kilopascals. What volume will the gas obtain at 68.7 kPa if the temperature remains constant? Well, due to the fact that the pressure changed and the temperature remained constant, we would have to say that this is a demonstration of Boyle's law. That helps us realize what should happen to the volume of gas. So it asks us how will the volume change? So it's question mark volume. You start with the initial volume, which is 118 milliliters. And now we're going to multiply it by a pressure ratio, which would tell us which direction the law states. For example, in this case, the pressure went from 84.9 to 68.7, which means that the pressure went down. According to Boyle's law, when this happens, the volume should go up. When you release pressure, the volume of the gas should increase, as long as the temperature remains the same. So this is what we want to happen to the initial volume. We want the volume to increase. So in order to do that, I place a larger number in the numerator, which is 84.9 kilopascals, and the smaller number, 68.7 kilopascals, in the denominator. So in that case, that's going to be a fraction that's greater than the number 1. So of course, when multiplied by 118, that volume should go up. And the answer is 146 milliliters. Great. Okay, now problem number 2 says we have 6.44 liters of neon gas, and it's collected at 17.2 degrees Celsius. It's asking us to find the volume if we change the temperature to negative 16.9. Notice that the pressure remains constant. The pressure does not change. So this is an example of Charles' law. And Charles says that if you change the temperature, the volume will change in the same direction. So if you decrease temperature, you decrease volume. If you increase temperature, you increase volume. Now, in doing gas law problems, we have to use the Kelvin scale, because if we were to keep this negative number in doing our math, dividing and multiplying, we would end up with a negative volume. And so we can't have a negative volume. So we have to change these temperatures to Kelvin scale. So you always add, the formula is, if you want the Kelvin temperature, you must have the Celsius temperature and add 273. Notice that this is a whole number, 273. So if we happen to have a decimal, using sig figs, we use the least precise measurement, which means our temperature can only be a whole number. So for the example of 17.2 degrees, our temperature is 290 degrees. And for our negative 16.9, that temperature is 256 Kelvin. So those are the temperatures we need to use in the problem. So we're trying to find how the volume changed. The initial volume is 6.44 liters. And again, we're going to multiply it by a temperature ratio in the direction we want the volume to change. So the temperature went down, the volume must go down. So this is what we want to happen. And so we will place the 256 in the numerator, the 290 in the denominator, seeing that that is a fraction that is going to be less than number 1, hence decreasing our volume. And our volume changes to 5.68 liters. Okay, I think you can see by doing those problems that concept is not difficult. You can practice them to know which law is which. And so problems 3 through 9 are the same type of problems. They're either Boyle's or Charles' law. And so you should be able to figure those out and possibly come to class and I'll give you the answers. And that way you can tell if you did them correctly. But I'd like to go down to problem number 10. Problem number 10 is a combined gas law. Notice at the top it says we have problems with Boyle's law, Charles' law, and combined gas law. And the combined gas law is just placing Charles' law and Boyle's law in the same problem. In other words, there is no constant in temperature. Temperature is not constant, pressure is not constant, and volume is not constant. The only thing that is constant is the number of moles of gas, or the number of atoms or molecules. In other words, you can't add more gas. So let's try problem 10. I'm going to move the sheet so we can see that. And there we have problem number 10 says, if a sample of a gas has a volume of 505 milliliters, the temperature is 10.3 Celsius. We'll have to change that to Kelvin. The pressure is 91.1 kilopascals. What will its volume be if we change it to standard temperature and pressure? So we're changing both temperature and pressure. So this is the combined gas law. And so what is standard temperature? Temperature equals 273 Kelvin, and pressure is 101.3 kPa. Now we do have to change the temperature here, and if you took 273 plus 10.3, you get 283 Kelvin. And of course, this is already in a unit of kilopascal, so there's no change there. So they're asking what's the new volume. So then again, it is question mark volume. How did it change? Start with the initial volume, 505 milliliters. Okay, so let's do the temperature change first. What happened to temperature? Temperature went from 283 to 273. So temperature went down, which means volume went down. So according to Charles' law, we need to make the volume go down. So we'll put the 273 in the numerator and the 283 in the denominator. Next is what happened to pressure. Pressure went from 91 kPa to 101.3. So the pressure went up. And according to Boyle's law, the volume must go down. So we need this to happen again. The volume is going to go down even more. So we put the 91.1 kPa in the numerator and the 101.3 because we want to have the effect of bringing down the volume, canceling our units of temperature, canceling our unit of pressure, and doing our math. Our volume is 438 milliliters. Notice we want the volume to go down in the problem. We started with 505, ended up with 438, and so it makes sense. Okay, I think you should be able to do the rest of the problems on your own. Hopefully this explanation made the math clear, and then after we do these problems, we'll move on to the ideal gas law. Okay, good luck.